Okay, shall I start?
Yes, I will say a few words, then you can start, ok?
Ok.
Muito boa tarde a todos. Vamos dar início à nossa palestra. A palestrante é a professora Letizia Tanca, é professora catedrática na Politécnico de Milão desde 2001, docente de bases de dados e tecnologias para sistemas de informação, autora de mais do que 200 papers em áreas de base de dados, Big Data Analysis e entre outras. Ela fez parte da Associação Informática Europeia, recentemente esteve também como vice-presidente da Italian Group of Computer Engineering Academics. Hoje o tema da palestra é sobre a gestão de dados como suporte para a ciência de dados, um exemplo baseado em sustentabilidade. A professora Letícia vai falar, no chat podem ver um link onde está disponível a apresentação que ela vai fazer e contém também alguns exercícios para que se possa praticar. Então vamos dar início à palestra. Professora Letícia, please, you can go on.
Okay, thank you very much. It's very nice because I more or less understand what you say because Portuguese is almost Italian, so
yes, it's a little bit simple. Thank you, please.
But it's nice to hear what you say also in Portuguese. Okay, so I will take away my video so that also the transmission may be easier. And I will start. So actually, I hope that the people who listen don't find these things that I will say old, because this is something also a bit, let's say, I'm mixing some traditional and basic things of data management with also some more messages. So we will see how it works. Okay. First of all, one point is the following. We should be very, when we speak about data, we should be very careful about what we do with the data, because nowadays lots of algorithms are used, for instance, to learn things from data. No? So for instance, you have a huge amount of data and you, from the past of the admissions of the students in a certain university, and you want to teach, you want the machine to learn how to admit students, to accept students in the university based on the past experience. The problem is that probably in the last 10 or 15 years, very few women were accepted in the university, very few people, very few colored people, very few people from Latin America, etc. were accepted because there was some kind of bias. And so also what will be learned by the machine will be that these people have to be excluded. And so what we have to do is to have data that are not only quality data, but also ethical data, for instance, because otherwise the machines will learn a behavior that is not ethical. This is just a parenthesis because I'm not going to speak about ethics today, but just to say that whenever you give to the machine will learn. So if the data are of bad quality, the machine will learn something wrong. There are a lot of examples of this. For instance, the fact that a machine that was, it was an automatic weapon that recognized targets for the war, and at a certain point, I don't know how, this machine, this algorithm misunderstood a bus full of children by how is it called? By an ostrich. Okay, so finally it was an animal for the machine, and it fired and it destroyed a bus full of people. Okay, so we really have to have very good quality data, because otherwise what we do is something very that can be also very dangerous. Okay, this is let's say a premise to say that data have to be cured, they have to be polished, they have to be in a very good condition in order to use them in the appropriate way. Now, what is the cycle to arrive at doing data analysis, data science, etc. Initially, you acquire the data, then you extract the information that is most interesting, because initially you find that your data is in 2 or 3 data sources, for instance. After that, you extract the interesting data from the appropriate data sources. You clean them in the sense that you create a set of data that is of good quality. Then you might annotate the data by introducing some information, some metadata that can help you for the rest of the processing. Then, if you have more than one source of information, you have to integrate these sources. This is also something that I normally teach, and if you are curious, we can have another lecture, but this is not what I'm talking about today. And then, after that, when you have the integrated and good quality data, then you start with your analytics, you start with your modeling, machine learning, whatever you do to obtain your result. And then you can interpret the data that you have, the results that you have extracted. So it is a difficult cycle. And what I'm going to tell you are 2 things today. One is an example of the use of data management techniques for something that is very application oriented, and it is, I hope, also an example that may interest you. And then I will also teach you, so besides this example, I will teach you how to design reliable data schemas in order for the analysts to have a clean set of data from which they can extract information. One thing that I wanted to tell you is please interrupt me whenever I say something that is not clear, because this is part of the lecture. It's not a problem if you interrupt. Whenever you want to ask questions, you can, okay? Okay, so now I give you an example of use of data that was not very, let's say, was also taught some years ago, but now we have the possibility to give to these users good data, okay? In particular, we speak about sustainability. Sustainability is the problem of a lot of parts of the world. So we have some information like that by 2050, 75% of the world will live in cities, and also there will be the problem that many of these people will be in very, let's say, in houses that are not adequate. They are slums, and so people will live not very comfortably. So my colleagues, in particular Professor Massimo Tali, who is the person that I'm thanking in this slide, and you will see more about that, together with a number of colleagues, have been studying how to improve the urban landscape, let's say the urban organization, in order to make cities more livable, okay? And to do this, initially they study number of data that are interesting about the city, and let's say measures by means of some indicators what are the sides, the aspects that are negative, and try to improve by means of improving those indicators, try to let's say to advise the city rulers, the city, the mayor, some of these people, the mayor of the city, to modify some parts of the city in order for it to be more livable. Okay, so this is an example that I'm going to give you, and these colleagues of mine are colleagues from Politécnico who are interested in this part, but they are architects, so they use the data, but they don't know how to use the data in an appropriate way, and that's why we are collaborating in this period. So we need a way to understand this environment in order to improve it by means of architectural techniques of course, but in order to understand, we use the data, okay? So these people work at this the design lab at Politécnico di Milano. It's called IMM. I think it means integrated modification methodology. That's what what IMM means. Massimo Tadi is the director of this group, and then there are a number of interesting people like Hadi Zaleh, Andrea Biraghi, and Tao Dong, who are people that work with Massimo since a long time. Again, if you are interested, I can also ask some of them to give you a lecture on this topic. That is not my topic, because they are not from computer science, they are from architecture. Okay. Now, what is IMM? IMM is a methodology that aims at improving the environmental performance by modifying the structural characteristics. So what they do is to study a number of topics, like, for instance, there are all these parameters, let's say, the attributes that are data that are to be analyzed about the physical context of the city. These attributes, by elaborating on these attributes, you obtain the matrix, and these matrix represent different characteristics of the territory. For instance, how far is the closest green area? And then there are some categories that give the impression of the city, in the sense, for instance, permeability. That means how far are buildings from each other? Can you move among the buildings? Are they so close that you cannot even move with a car? The relationship between the street network and the special components. There are a number of other categories like this. And then from these information, these three groups of information, these friends of mine extract what is called the indicators, that are actually numbers, okay, that should respect should be within a certain range to be acceptable, and if they are not within that range, they should be modified, okay. And then there are also families of actions that the designers can do can advise, let's say, in order for these indicators to become better, to be improved, okay. So this is a very, let's say, mathematical approach, if you want, for these architects, because they are used to reason in a more qualitative way, not in this quantitative way, but by means of these characteristics, they have built a very large Excel sheet, and they extract a number of information. The problem is that this Excel sheet is full of problems, in the sense that there are many repetitions, there are many things that should be equal in the same value should be in many places, but actually the same value is not, in the sense that in these places where there should be the same datum, in fact, there are differences from one place to the other. The Excel sheet is very big, and so it is difficult to extract exactly what is needed in order to do the analysis. So these friends asked us to help them to systematize the data in order for them to have a set of tables that they can combine together in order to extract the right information. And actually, these people, I wanted just wanted to tell you that they initiated, but actually I think it was not finally financed, unfortunately, that they initiated this with the objective of improve the situation, a project to use IMM to improve the city of Cayman, that you know better than I, because it's a city in Mozambique. I think you know it, right? Somebody can answer me?
Yes, we know Quilimane.
Know it, okay. So they started with this idea of working in Quilimane, but I think the thing went not on because there was a problem with financing, as usual, because you know, we are all with the problem finding money for our projects, but they had studied Quelimane a lot, and so there was problems with as you know, there are problems with floods, there are problems with the life of people there, and they wanted to improve it. So maybe it will start again, we will see. Anyway, the idea is that these the objectives are inspired by the famous SDGs, the Sustainable Development Goals of the European Community. So no poverty, clean water and sanitation, etc., etc. But they are specifically oriented to the sustainable cities and communities. Okay, so that's their main objective, and we are helping them with their data because I'm not an architect, but we are working with them on that point. Okay. So their idea is that cities are complex adaptive systems. There is heterogeneity. There is the problem of connection between places of the city. There is the problem that cities become greater and greater. And so actually when the city is small, you can control it and things go well. But when they become very, very big, it is very difficult to control them, and problems become much different with respect to the problems that were there before. And often you don't know when something is the cause of some effect, because the effect also becomes the cause of another effect, and things are mixed, and cities change in a way that is not controllable in a way. So the idea is that IMM should attack all those problems. This is another slide to show that a city is a system, and so it's a complex system, and with the tools to approach the complex systems problems, they are trying to approach them. Often, on the other hand, the problem is that things are considered one by one. Okay, the problems are considered one by one, but the problem is instead that you cannot consider the problems one by one, because the system is complex and things influence each other. And so you should try to look at the thing in a global way instead of looking at one problem at a time. So IMM tries, and indeed it is called integrated methodology, because it tries to attach the problem from that point of view. But that makes also it very complex. Okay, so the management of the data is very complex. Now, this is a figure that they use to show the components. The city is formed by areas that are built, by voids that can be a small lake or a square or a street, by the types of uses that you use for the buildings, for instance, and by the problem of mobility. And these are what I was calling the key categories before. So porosity, proximity, how things are close to each other, how areas of the city are diverse with respect to each other, what is the way you can interact with the city, what is the interface. I mean, these are a number of aspects, and this is how are they related to the social problems, the environmental problems, the economic problems, and the management. Okay, so that's what they are going to study. But again, now I will start with what I really know, that is data management. And so the idea is that they want to, from the raw data, they want to get the information that is able for them to reach the possibility to do predictions on the fact that, for instance, if you apply such and such change, then this is the way in which the city will change. So instead of applying directly the changes to the city, one can experiment with the data, saying, okay, if I change this one of these parameters that we are saying here, how can I improve the performances by changing this parameter? And then, so they obtain the result by means of data analysis, and then they see what is the best way to attack a certain problem. Okay, so that's the idea. Okay, so let's go back to what I started with. Sorry, I'm just going to open the window. Just a minute. It is very hot today. Okay, sorry. So now what is the idea? The idea is acquire all this data about a city, extract it from the data sets where this data is, cleaning these data sets, annotate them in order to make them more clear when we want to integrate it, put all these data sets together, and then start the analysis of the data. But first of all, we have to have data that are well designed. Okay, so this part that is acquisition and extraction and cleaning has to do with the way the data has been organized also in these data sets that we could use for the analysis. So, okay, and so what I'm going to talk about will be the use of the semantics of the data, of the meaning of the data, in order to design the data in a clear way. Now I have a question for you. Have you ever studied data design, data management, data design in the sense of how to design a good database?
Yes, Professor.
So you know, for instance, the entity relationship model? Yes,
we're calling, we have some steps to have, if it is what I think about, we have some steps to get.
Because my problem is
can you understand me, Professor?
Sorry, no, because I mean, I wanted to show you an example of the entity relationship schema, because otherwise I'm going to explain to you how to design a database according to this cycle. Okay. You already know it or not? To design this conceptual schema that is a graphical schema and then to transform it into tables.
Yes, we know that. We know that.
You know already. Oh, this is a problem because this is what I had prepared for today. So,
but anyway, you can explain, teacher, no problem. But I think that among of us, we know this.
Yeah, Tikongolo, speak for yourself.
Excuse me? No,
I was okay. Asking my colleague to speak for himself.
Okay.
Okay, so that's
go on, Professor.
So not all of you know it.
Yeah, not all of us. We come from many different specialities here.
Oh, okay.
So it will be very useful.
Oh, very good.
For me and colleague Inacio and others, we teach in this subject. So we have a very good idea of what's to come, but there is a lot of colleagues from other areas here.
Okay.
From other areas.
So, okay. So I'm sorry for the people who know it. There is also Inacio. I met Inacio some days ago, and I know that he knows these things. Okay. Anyway, if I'm too slow, you tell me. Okay. So if I'm really saying things that are very, very obvious for you, maybe we can do more exercises, for instance, in order to, and we can spend also a little bit more time on the conclusion, that is, because I wanted to show you, what I want to show you is first the methodology, and then how we represented these elements of IMM that I have been talking to you about. So if you think that I'm very slow, and you please interrupt. So the people that are supposed not to know things well, if they also think that I am slow, please tell me to go quickly, okay? There's no problem. Okay, so the idea is that databases, one thing that I want to tell you initially is the following. For a long time in the area of databases, we have been using relational databases, that are databases that use tables, and these tables must be designed in a certain way. Relational database management systems are very important because they are softwares that can manage the data in such a way that you can prevent the data from becoming dirty, because you can write constraints that the data have to respect, and in such a way the user cannot, or the user on an application cannot introduce things that are contradictory, for instance, because the data are organized in tables in such a way as not to have redundancies, because when you have duplicates of the same datum, it is possible that when somebody modifies the datum, it is modified in one place and in the other place it is not modified, side, and so there will be contradictions in the databases. So relational databases, even if now data clouds, things like Hadoop, etc., are very fashionable, relational databases are still very important for the applications that are critical. Okay, so for instance, in a bank, you have the system that is a relational DBMS that controls in such a way that errors are happen very seldom. While if you have another collection of data, like, I don't know, for instance, when you are collecting sensors that collect the data of in the mountains or somewhere else, or maybe something that collects the quality of the air or whatever, then contradictions are not so critical. You know, when there is money at stake and when there is human lives at stake, it is very important to have very well controlled databases, because you could have errors that put in peril either the money or human lives. I think that human lives are more important than the money, and I think also in both cases we have very reliable database management systems. And I still think that organizing the data in such a way that is well designed by means of relational databases, at least at the beginning, makes things much more secure, let's say. And this is also what I transmitted to my colleagues of architecture. So the final thing that I will show you today will be, as I was telling you, the entity relationship and the relational schema for the IMM data. And in the meantime, let's go through database design. So database design is one of the many activities for developing an information system in an organization. And it also helps us to clarify the concepts that are at stake in our problem, what we want to represent. And now, so we will reason more from the point of view of concepts initially, because first of all, we want to, for instance, when I go to the employees of the bank and I am the designer, I am the person that has to design the database, I will ask them what are the most important concepts, not the most important data, but most important concepts, okay? In order, so what are the concepts? The clients, the orders, the warehouse where the products are stored, the invoices. These are concepts initially, okay? Because these are things that we want to know what are their relevant characteristics. And so there is this interesting model that is called the entity relationship model. It is a conceptual model that helps us to understand what are the most important aspects of what we want to design. And then we transform them into schemas of tables, okay? And the interesting thing is that once we have understood very well these concepts, we represent them graphically in this way with our entity relationship model, translating these drawings, let's say, into the schemas of the tables is very easy. So this is what I will talk about today. So initially we will speak about, so the entity relationship model is for conceptual design. So for this high level conceptualization that allows us to understand what are the main elements of our database. Then the logical design is when we translate the conceptual schema into a logical schema. That means the schemas of the tables, the schemas of the tables where the data will be stored. And then there are also other data structures that you surely also have studied, that are the data structures that will be stored into the disk, into the cloud, whenever, whatever. And so they have often a tree-based structure, or they are just files, etc. This is something that we won't touch at all, because this is taken care of by the DBMS, and as designers we are not interested in. We would be interested in that if we were those that design and implement the database management system. But now we are speaking about designing the database for a specific application. So we have to distinguish the The fact that, for instance, this is Politécnico de Milano. I designed the database for Politécnico. It means that I'm going to decide how the tables containing the information for Politécnico are structured, are organized. But these tables then will be managed by a system that is a software system, that is the database management system, that will take care of optimizing the access of receiving the queries, optimizing the access to information, etc., etc. So first of all, we have to distinguish between the database, that is the data, the set of data, and the database management system, that is the system, the software system that manages the set of data. Okay, that's the most important thing. Today, we will speak about how to design the tables of a database. First of all, we go through this part of the entity relationship model. The entity relationship model, you have also seen from that small figure that I was showing you, has these three fundamental elements. Then there are more elements, but these are the fundamental ones. First of all, the entities. What is an entity? An entity represents a set of objects that I want to store in the database. So for instance, person, okay? For instance, student. For instance, room. Okay, for instance, book. It depends what my database is talking about and all the elements that will be stored in the database. Okay, then we also consider the relationships. The graphical tool for representing the relationships is this diamond. Okay, and a relationship represents exactly a relationship between two entities, for instance. For instance, I could have two entities, person and city, okay? And there is a relationship that says person lives in city. Now, what is important for you to understand, for those who have never seen this, is that the entity person is considered as a set that contains all the persons that I want to put in the database, okay? So this represents the concept of person, and is a placeholder to say, okay, my database will contain persons, okay? My database will contain cities, and there will be an entity that is called city. They represent the set of persons that are in the database, the set of cities that are in the database, and also the relationships between these persons, those persons that live in a certain city, okay? And then the last but not the least is attribute. Attribute represents the properties of these objects that are in the entities. So for instance, a person can have a name, can have a telephone number, can have a social security number, and things like those, okay? So these are the main elements of the entity relationship model. I will show you examples as we go on. Okay, now you have, I always have these slides that say what I already said. Okay, so they represent classes of objects that have properties in common, etc. These objects have properties in common. So examples of entities are city, department, building, street, etc. And they represent the sets of objects that are in the database. Now, when we speak about an instance, we say an occurrence or an instance of an entity, we are speaking about a specific object that is in the class of that entity. So for instance, if we are speaking about the database of Politécnico, and there is an entity employee, okay, I will be one of the elements of the entity employee, okay? So I am an instance of the element employee, but I'm also an instance of the element of the entity person, because I am a person and I am an employee. Okay, if we speak about the street where the Politécnico is, then that street will be one of the elements of the class of the entity street. Okay, so an entity is a class of objects. Questions on this? Clear? I go. Okay, from here we move to relationships. They represent logical links between one or more entities and represent the links between those instances of the entities that are related. So, for instance, if you have something like person lives in a city, there are two entities, person and city, there is a relationship, and so the person myself, that I am in the class of the persons, I am related to Milan because I live in Milan. Okay, so they are links between those elements that are actually related in reality, and that relationship will be stored in the database. And then the attributes describe properties of the entities, as I was telling you before. Okay, surname, salary, age, etc., etc. They are attributes of the objects that are in the entity. So this is a small example, very small. I have 3 entities here. The entity employee, this is representing, let's say, a database of companies with their employees. Okay, so I have an entity employee. The entity employee has 2 attributes, name and ID. This is a very simplified example. So what does it mean? It means that each element of this entity has a name and has an ID. Okay, typically ID will distinguish the employee from all the other employees that might have the same name, but with the ID we distinguish. Sorry, I'm closing the window now because there is noise. Okay, so now there is another entity that is department, and we have also a relationship that links those each employee with the department where he or she works. Okay, then the department has a number and has a name, and the department belongs to a company. So there is another relationship between department and company. So each department belongs to one company, and the company will be related to all the departments that are part of that company. And the company has 3 attributes: the name, the address, and the phone number. Okay, questions? Okay, so let's go on. And here I have an example of a conceptual schema that is a bit richer than the first example. Okay, so first of all, we read this text because this text is giving me the requirements for the schema. Here you will see also something that I have not explained. You will see some signs that I have not explained up to now. Now we comment only on the things that we have explained. And then we go on. I explain something else, and then we go back to this schema again. Okay. Now, Polypatents is an organization. And this organization grants technological patents to companies in the United States. Each patent may be assigned to multiple companies. So companies could get together in order to produce a patent, okay? And is associated with one or more inventors, this patent, okay? Sorry, there is a sign there. Okay, no problem. This yellow thing does not mean anything. It's something that I did by mistake. Okay, then inventors are the people that have participated in the invention that has been patented. Polypatents stores the patent-related data in a relational database. And so we have to design this database, okay? So the patent is related to the inventor. So this is a set of people that are inventors of patents, okay? The patent is also related to the assignee. Assignee is the company that is taking the patents, okay? So this is the idea of the assignee, this is the name. Then there is also the city where the company is residing. And also we also have an information about what is the city where the inventor resides, okay? Then another interesting thing is that you see here we have a relationship that is a cyclic relationship. So it is on the same entity. What does it mean? It means that one patent could cite another one, because you have a patent about, for instance, a specific mechanism, a specific robot, for instance, but this makes reference to another robot from which that is a part of the robot that I've been patenting now, okay? So patents can refer to each other because they could use let's say, could exploit things that have been published with a previous patent. Okay, you see that the attributes are, in the case of the patent, patent ID, title, grant date, abstract of the patent that describes the patent, and the CPC category. I'm sorry, but I don't remember what it means. Anyway, it is important because probably it's the category of the patent in the sense of which area is it referring to, which scientific area it is. Then there is the inventor that has an ID, first name and a last name. Then there is the city name and country to which it belongs, and the assignee, that is the company that has an ID and a name. Okay, so these are the things we have been speaking about up to now. And so if you understand what I've shown here, I can go on. Everything is crystal clear? I'm going. Okay. So now I speak about another concept, that is the concept of cardinality. What is the concept of cardinality? Let's consider these two sets. This is the set of the students. This is not entity relationship. This is just, Venn diagrams. So I mean Venn's diagram. So I'm representing a set by means of a circle with some elements inside. Okay, so this is exactly what we use in set theory. So I have a set of students and I have a set of exams, and these are the links between the students and the exam. So for instance, this student has taken 2 exams. Okay, this student only one. And this exam has been taken by more than one student, okay, already. So this is, of course, very, very simple. Normally things are more complex because there are many more students and many more exams and many more relationships, okay? But this is a graphical set-oriented, let's say, representation of 2 classes, so 2 entities, and the relationships between these 2 entities, okay? Now, what is interesting is that this student, for instance, is related to two objects here, to 2 exams here. Then there is also a student that is related only to 1, but also an exam can be related to more than 1 student, okay? So actually the relationship between these 2 sets through the relationship of taking the exam or passing the exam, for instance, between these 2 sets is a relationship that allows one student to be related to none, because he or she has not taken any exam yet, or to 1 or even 2 more exams. And the same is for the exams too. It can be related to no student for the beginning, and then to more and more students. So we represent this by means of these graphics. So for instance, let's think about the exams. For instance, the student takes the exam for a certain course, okay, and here we can store the mark. So here you can also see something interesting, because I put in this case I put an attribute on the relationship. It is possible to put attributes on the relationships. In which case? In the case in which this attribute is related to the pair of objects, because the mark is not related to the student. Because if it is related to the student, to which course does it refer? And if I relate the mark to the course, for which student is it the mark? Okay, so actually the mark is related to the pair student exam, student course. Okay, so that's why I put it on the relationship, because it is an attribute of both elements of the student and the course. Okay, so that's the idea. Now I say, okay, given a student, this student can take 1 or more exams for 1 or n courses. This n is a generic n that we use everywhere, so it's not the same n. It's just to say that it is a generic number. Okay. And given a course, this course can be, for this course, from 0 to n students can have taken the exam, okay? Of course, for the students that have taken the exam, we also have a mark, okay? Now I show you, is it clear up to now? Now I show you something else. I show you the case in which you have the same entities, the same relationship, but with the attributes put into different places. Okay? And I will explain to you why. First of all, we say, okay, given a product, the product can be delivered by one or more suppliers. This is the reality of this company. This company has for some products can have also more than one suppliers. Okay? Given a supplier, it can deliver one or more products. Okay? Now, what do I read from this? You see that product does not have attributes here because there will be attributes. Also the students, the course, they have attributes, but we didn't, let's say, we are not putting them here because I'm only putting the things that are relevant to what I'm saying. But of course, the product will have a name and a number of other attributes. Okay. Now, what do I read from this first graph, let's say? What I read here is the following, that given a supplier, that supplier for different products has always the same delivery time. So the supplier says, okay, whatever product I will give you, anyway, I will deliver it by 1 month or by 1 week, within 1 week. Okay, but it does not depend on the product. It depends just on the supplier, because the supplier has that time of delivery. Okay, and then the price can change because that supplier can sell a certain product for a certain price, but another supplier might have a different offer a different price for the same product. That's why the price is not on the product. It is on the supplier, it is on the relationship, because it depends on both. It's not on the supplier, because the supplier might supply more than one product, okay? And the price is not the same, of course. But it is on the pair for each product and for each supplier, there is a price, okay? Have you understood what I said? So I'm going to this case. This case is different because I'm expressing something else. First of all, I say, okay, that the product, the price that we consider, my company, the company that is the owner of this database, considers to pay a certain price for the product, okay? This is the price that the company is maximum wants to spend, okay? But according to the supplier, maybe there might be a different discount. And also the supplier has a different delivery time for each product. It is not the same delivery time for all products, like here. Why do I read this? Because I see that the delivery time now is on the deliver relationship. So it doesn't depend only on the supplier, but it depends also on the product. Because maybe the supplier has has the different times of production for the different products, or different times for itself for finding the product, and so the delivery time might be different. Given a product and given a supplier, the delivery time can be different even for the same product and different suppliers. Okay, and the same. Okay, so. Moreover, there is a discount that depends on the product and the supplier, a discount on the initial price. Okay, so this is another way to represent the same thing. But the thing is a bit different, because in this case we can see that the price is there is a maximum price that the company wants to spend. So here we have a price that depends on the supplier and the product, and then, okay, we can decide not to take it. But here the system also knows what is the maximum price that the company wants to spend, because only the discount is allowed. Otherwise, a supplier that provides the product for a too great price will not be accepted. Okay, so you see that in in this way, by putting attributes in different places, we can represent different situations. This is the thing that I wanted you to understand. And so it is a very sophisticated model because according to the situation, we can represent very different situations. Do you want to ask something? I see that there are maybe. Okay, so. No, I thought there were some questions for me, but I don't see questions for me. Please speak up when you have questions. Okay. So the attributes also can have cardinalities, but the default of the attribute cardinalities is 1, 1. So that means that when we don't write the cardinality, the attribute, there must be the attribute and it has cardinality 1, maximum 1. But there are also attributes that have more than, as the cardinality more than 1. I don't have the I don't have an example here for the attributes. Let me see. I also only have cardinalities for relationships. No, yeah. But for instance, one could think that for instance, if the patent could have more than 1 category, here I would say 1 n categories, okay? Or maybe up to 3 categories, I would write 1, 3 categories, okay? So also attributes can have the cardinalities. Then another element that is very important are the identifiers. What are the identifiers? Identifiers are elements that allow us to identify unambiguously the elements of the entity. So, for instance, let's go back again to our example. The patent ID is the identifier of the patents. There are no 2 patents that have the same ID. There are no 2 companies that have the same ID. There are no 2 cities that have the same name. Okay, here we are saying that in our database there will never be 2 cities with the same name. There are, for instance, you know, in the United States there is Paris that is in Texas. And now, so either we write Paris, Texas directly there so that we can distinguish it from Paris, France, or we have to say that the city name is not enough to identify the city. We should also use the country, okay, in order to identify it. And so we should have an attribute. I will show you some examples that is taken from an identifier that is based on more than 1 attribute. And also the inventor ID is only 1. Okay, and this is an example. For instance, the person that has name, a number of other attributes, and then social security number is the identifier. But for instance, in some cases, we don't have the social security number. We are in a less formal situation in which we know name, surname, and birth date, for instance. And so we can use these 3 to identify the person. Because it is difficult that 2 different persons have the same name, surname, and also birth date. Okay, so we can use more than 1 attribute to identify an entity when some surely single attribute is not present. Okay, if we don't have the social security number, then we say, okay, let's use surname, name, and birth date. Okay, for instance, a hotel could be identified by the name and the city. Because often there are hotels that have the same name. I don't know, for instance, Marriott or all these hotels that have that are chains of hotels, and so we have okay, Marriott Milan, Marriott Mozambique, etc., not Mozambique. In this moment I forget your capital, which is a very, very unpolite and but more than that, I'm worried about myself because I forget a lot of things. So it's my head that doesn't work. Okay. Anyway, office, number, company, and city constitute the office ID. But if I am in the database of the company, then the company and the city are not necessary because, and so I can use only the office number. Within the same company, it's useless to put the company in the identifier. But if we are speaking about offices within a city, for instance, in another organization, like for instance, here in Milan, here in Politécnico, we have relationships with some offices because of other companies. And so we keep the number of the office, the company, and the city. Okay. Questions? Okay. So here again is polypatents, but the identifier you already saw, and so we don't have to see it again. Now, there is something a bit delicate because it may happen that an entity does not have enough attributes to be identified. For instance, the transaction, one transaction within a bank account, a movement in a bank account when you add or subtract money, then it needs also the bank account to be identified because there will be number 1, number 2, number 3 within that account. But then in order to identify the specific transaction within the bank, we need the bank account to which the transaction refers and its number. Okay? So what does it mean? It means that this entity transaction is a weak entity because its specific attributes are not sufficient to identify it. Okay? And so we use a strong entity on which it depends. And we call it external identification. And we use this graphical. So we within the entity rectangle, we draw another rectangle, okay? And we also draw, now the red thing is not that you have to color it in red. It's only to, let's say, underline for you what are what is the new notation, okay? The new notation is add another rectangle within the entity rectangle and add this to say that the transaction number and the bank account to which it belongs are used together to identify the transaction. Mind that we can do this only because a transaction belongs to only one bank account. I cannot use a relationship where the transaction, where the weak entity is related to in a relationship where there is more than one account, for instance, because otherwise I cannot identify it. So always when I have these weak entities, I have to have a relationship that is 1-1. Otherwise I couldn't. So minimum 1, maximum 1. There must always be an account for this transaction, and it must be only one in order for the transaction to be identified correctly. Okay? How is it for you now? Do you understand that? Is it clear? Because I'm going very quickly, so I'm worried about that. Okay, so let's go to another example. For instance, a street, you know, you have many streets in a city, you can have many streets that have the same name. Sorry, in a country, okay? Because, for instance, I don't know, there is always, you know, in countries there are the names of the streets that are entitled to the country heroes. For instance, in Italy, we have Garibaldi. There is a Garibaldi street in each city of Italy, okay? Always. Corso Garibaldi, Via Garibaldi. There is always something for Garibaldi. Or Michelangelo, huh? An artist, okay? So how do you distinguish a city, a street of a city from the street with the same name in another city? You say, okay, we have the street name and we have the city it belongs to, because of course you don't give the same name to two streets in the same city, okay? So I can say Via Michelangelo in Milan and Via Michelangelo in Rome and Via Michelangelo in Salerno, that is my city, for instance, okay? So it's another example of weak entity. The name of the street is not enough, but the name of the street together with the city can single out exactly that street of that city. Okay, and now I have another entity relationship example. But I want you to really tell me if there is something up to now that you have not understood. I mean, it's not your fault if you don't understand. I'm very quick and probably I haven't explained well. So it's important that you say it because I can explain it better. Everything crystal clear. Okay, very good. I'm very happy about that. So let's see another entity, another conceptual design. These are rather simple, then I leave you with something a little bit more complex. And so for the students who really don't know this tool, this thing of entity relationship schemas, they can do exercises and then we can make an appointment, for instance, and you can show me your exercises and I can correct it. Okay, for the moment, this is also something that I'm showing you. So Polycoach is a transport company that offers a coach service in Italy. It issues tickets for the travels. The tickets are strictly personal and may comprehend multiple travels. So given a customer that wants to buy tickets for a number of travels, possibly the company can give to this person, for instance, a discount. And so we put together the package of the tickets, and that package of tickets maybe costs less than a single ticket. I mean, than the sum of the single tickets. Okay. The price of a specific travel may vary depending on the other travels with which it is sold. Therefore, the total price cannot be decomposed into the prices of the component travels. Well, that's what I just said. It's not just the sum of the prices of the component travels. And this is the way we represent it, okay? This is the database of the company. So there will be the vehicles of the company, and for each vehicle there are a number of information, the plate number, the manufacturer, Skoda, I don't know, Fiat or whatever company. Then the displacement, that means how big, how large it is, how much space it occupies on the pavement, the number of seats, the number of places that there are where people can sit, okay? Then there are the travels, the travel ID, the date, the departure city, the length in miles, and the destination city, departure and destination city for a certain travel. So given a travel, it is performed by one and only one vehicle, okay? Because that is the decision that for a travel, there will be only one vehicle. There is not possibility to change vehicle unless there is an accident, for instance, okay? Given a vehicle, of course, it can serve multiple travels, okay? Not at the same time, but in the history, it can have served multiple travels, and also there might be travels that are planned, and so also, and we already know what is the vehicle that is assigned to them, okay? So in the past and in the future, we keep track of which vehicle served which travels. Then there is the customer. The customer has an ID, a social security number. You can see that here there was a decision to design the database in such a way that also there is also a customer ID, even if the social security number would be sufficient to identify the customer. Okay, but this is something that depends on what the company Polycoach wants for its database. They have a customer ID that they assign independently of the fact that the customer has also a social security number. They want to put an identifier to their customers, okay? Then there is social security number, the name, and the date of birth. And then there is the ticket. The ticket is a weak entity of the customer, in the sense that there is a timestamp for the purchase of the ticket, and there is the customer that is used to identify together with the timestamp of the purchase. So that means that this ticket is the one that was bought by that customer. Each ticket is the one that was bought by the specific customer at a certain time. So it is an identifier. It identifies the ticket uniquely. Why there is this thing? Because they want to have a different price if depending on the travels that are collected within this ticket. Because here in the specifications, you see that the tickets are strictly personal and also may comprehend multiple travels. So given a ticket, there might be more than one travel, okay? And there is a price that depends on this travel and also maybe on the customer, there will be a discount or whatever. And then the class, whether it is first class or second class, for instance, okay? So this is the entity relationship schema of this database. Questions? Okay. The last but not least element is the generalization hierarchies. I'm going to the example directly. Generalization hierarchy is represents the following thing. Suppose that I want to represent persons, but I also want to represent, since in my database, there are things that are related only to the men and things that are related only to the women, I also want to put into evidence that when the person is a man or a woman, because for instance, for the woman, I also have the attribute maternity status that does not apply to men. Okay, but also maybe there will be here, no, because it is just an example, there may be many relationships that are related only to women and many relationships that are related only to men. And so that's why I want to make this distinction. In this case, I will have a class that actually contains men and women, and it is the class person. But in the entity person, I only, let's say, insert the attributes that are common to men and women. All men and women have a social security number. They all have a surname. They all have a name. They all have an address or something, some other attribute. But then there will be relationships and attributes that pertain only to men and relationships and attributes that pertain only to women. And so for those, I will attach them to these subclasses, we call them. Why? Because these are sets that when I put them together, form completely the person set, okay? And indeed, here you see TE. What does T mean? It means that the hierarchy is total in the sense that if I make the union of the class of men and of the class of women together, they completely cover the class of the persons. There are no persons that are neither men nor women, okay? All these persons, they all are either men or women. So this means that it is total. Exclusive means that there are no persons that are at the same time men and women. So there is these two things can be expressed in terms of sets by saying that the union of these two sets is exactly equal to this other set, to the set person, and this means total. And exclusive means the intersection of the set of men and the set of women is empty. Okay? So TE means the union covers completely the top class, and exclusive means that there are no elements in the intersection of these two sets. Other example, a company has external and internal collaborators. I have an entity collaborator. There will be an ID, a surname, a name, all these things that are true for all collaborators, but there are some internal collaborators, the ones that are paid by the month, and they are hired for forever till they are fired, but for the moment they are always there. And there is the monthly salary. And then the external collaborators that consider the salary by the hour, and because these people are paid by the hour, so there is a salary by the hour and up to how many hours I have collected up to now in the database. Okay, so this person has collected in this month 8 hours. Then tomorrow this person will work 2 more hours, and then this 8 will be updated to 10. At the end of the month, you see how many hours have been stored, and then the person is paid by multiplying that salary by the number of hours. Okay, so this is also totally exclusive because among the collaborators there are only internal and external collaborators, and if a collaborator is internal, he or she will not be external. Okay. So these are the properties of the generalization, and it is something that I already told you. Oh, no, sorry. Now I showed you only 2 examples of total exclusive. Actually, the generalization can be partial, okay? Because for instance, I could have an entity that is person, and the sub-entities are workers and students, okay? And of course, there are people who are neither workers nor students. So the cover is partial, okay? Because the coverage is partial because there are persons that are neither workers nor students, for instance, small children, okay? And also it is not total because, sorry, it is not total, it's partial, and it is not exclusive because there are people who work and study at the same time. So there will be student workers, and there might be persons that are neither students nor workers. So I say partial when there are elements on the upper entity that do not belong to any of the classes that are the sub-entities. And I say exclusive when the intersection is empty. If the intersection is not empty, I call it overlapping. Okay? Questions? Let's go on. So there are a number of exercises that I'm not going to, you have them in your slides, in the ones that I have shared with you, but I'm not commenting this because otherwise today we will not stay in our time. I want to show you how to translate an entity relationship schema into the relational model in order to see what are, because the final objective of our study is to produce the schemas of the tables in such a way that these tables will be safe from errors, because for instance, there will never be, if not strictly necessary, repetitions of the same thing. So that that information is only in a place, and when you update one, when you update it, it will not be necessary to update it into another place. And if there are 2 occurrences of that entity, of that value, the interesting thing is that the system will update also the other one when there are more than 2, because you can write it as a constraint and the system will do it. Okay, so relational model, what is the relational model? It is the way to represent data as tables. These, so we call this table a relation. Okay, it's called a relation. The names of the columns are called attributes, and the columns, okay, themselves will contain data related to the things that I want to represent. So for each of these rows, the rows are called tuples. So whenever you see, you hear me saying tuples, remember that I'm referring to the rows, okay? And for each of these, for instance, this is the database, this is the table that represents the professors in a certain university, okay? So there will be professor with ID 10-101, and this professor is called Srinivasan, the department name is computer science, and the salary is this. And then there will be Professor Wu, and the department name is finance, and this is his or her salary. And then Mozart, music, etc. It's Einstein, physics, as you can imagine, etc., etc. Okay, so this is the way to represent things. And if I want to say something else about these people and about, for instance, the courses, I could also have, let's reflect on this for a moment. Suppose that there is another column that is called course, okay? So Srivastanan is in the department of computer science. This is the salary, and then I put here also the name of the course that this professor teaches. What about the fact that this professor could teach more than one course? I only have one place here. So how can I represent it? I should say, for instance, course 1, course 2, course 3, a number of columns for each course that this person teaches. But maybe there are also professors that teach only one course. And for them, those columns will be empty. The best thing to do is to have another table that has the pair professor ID, course ID, and there you see always which person teaches which course, okay? And what is that table? That table represents the relationship of the entity relationship we have spoken about, okay? So finally, where do we want to go? We want to go to a place where each entity will give birth to a table, and maybe also some relationships will give birth to a table, to tables, okay? And you will see how. Okay, the set of allowed values for each attribute is called the domain of the attribute. Okay, so for instance, if the attribute is department name, the domain of the attribute is the set of all the departments of that university. Okay, and when we say that the domain is the set of the attributes of that university, it means that the system will control. If you write something, something else as the name of the department, the system will signal to you that it is an error, because the system only expects names of the departments of that university. Okay. Then the attribute values are atomic, that is indivisible. It means that in an attribute I cannot put more or two elements. The only case in which I can write something a little bit more complex is the date. I can put a date here and it is accepted as, I have to go quicker because Luciano told me that I'm very, very slow. Okay, so you know this, and so I'm going on. This is something about the domain of the attribute. The relations are unordered. A relation has a key that is the identifier of the table, and the identifier of the table can be only one attribute or more than one. And also we have foreign keys. The foreign keys are the ones by means of which the tables refer to other tables. So for instance, in that table, I was saying that contains the ID of the professor and the ID of the course. They refer to the tables of the professors and the course. Some elements could be, some attributes could have, and these are the foreign key constraints. Okay, this is an example of 3 tables. So I have data about the customer, data about the account, and then I have the table that puts together customers and account numbers. And so, as I was telling you about the professor and the course, it is the same. You have all the data about customers here, all the data about the account here, and the relationship between customer and account here. Anyway, you should tell me that I have to be quicker because you already know. It's not necessary that you tell Professor Baresi. Don't be shy. Okay, so how do we translate the entities and relationships into this? We have that the entities can be translated, each entity is translated into a table. This is the schema of the table. This table will have as name the name of the entity, as identifier the set of attributes that are the identifiers of the entity, and as attributes all the other attributes. Okay, so this is the way to translate an entity. To translate a relationship, I suppose that I already have 2 tables that have that represent entity E1 and entity E2. Okay, then the relationship is translated as the set, and maybe the relationship also has some attributes. I translate the relationship as a table that has as name the name of the relationship, and as a key the union of the 2 keys, the 2 identifiers of the 2 entities. Okay, so these are K11, K12, K1N, and K21, K22, K2L. Okay, this is the identifier of the relationship, and then the attributes of the relationship that are not in the identifier. Please stop me if I am too quick. So this is another example, and it is exactly as the previous one. And there is also an optimization of the translation, because when I have that an entity has the cardinality 1, 1 towards the other entity, then I can, in order to translate this relationship, I can import the key of E2 into the table E1, because to each element of E1, only one element of E2 will correspond. So I can import it here. So for instance, I have that I have the entity E1, the entity E2, but in the entity E1, you can see that I have imported, sorry, the key Q1, Q2, okay? That is the key of E2, okay? Okay. In order to translate the generalization hierarchies, I have 3 different types. Of translations. One is to translate it into 2 different entities by taking all these attributes and putting them on the entity, all these attributes and putting them on the entities below. Okay, so I forget that there is a generalization and I translate it only in 2 entities. This is only possible when the hierarchy is total and exclusive, because otherwise some elements would remain out. Then another possibility is that I translate these 2 entities, I put all the attributes on the entity above, and the attributes of these entities become optional. And the other possibility is that I produce 3 entities in which there is the father entity, let's say the top entity, and then there are 2 entities that are identified by the key of this entity, and they have their same attributes. So let's say, transforming E1 and E2 as if they were weak entities of entity E, because they inherit its identifier. Is it clear? Because this is not so obvious. I'm going fast, but I don't know whether you like it. Clear? I'm going on? Okay. So there is here the translation of the polycoach conceptual design here. So you can see how we translate it. First of all, we translate all the entities. Okay, so vehicle will be identified by plate number, manufacturer, displays, and then number of seats will be its attributes. Then travel, okay, but travel, you see that there is a 1-1 relationship here. So in order to translate also the relationship, I have the identifier of travel, all its attributes, but also I import the vehicle plate number, that is the identifier of the vehicle, because the travel is only performed by 1 vehicle, okay? Then the customer has the customer ID, social security number, birth date, and name, okay? Then the ticket is a weak entity, okay? So the ticket, in order to be identified, needs the timestamp, but also the identifier of the strong entity from which it depends, okay? So I have that ticket has customer ID, that is this one, purchase timestamp, class, and price, okay? And then you see that we have this relationship has already been translated because I imported the customer ID in here, since there is a 1-1 relationship here. This one also I imported the plate number in the travel, but this one is a M2N relationship, and so I have to translate it directly. So I have ticket travel, customer ID, purchase timestamp, and travel ID. That are the identifiers of these 2 entities, okay? Questions? Okay, now you see that there are all these IMM components. I'm almost finished because I want to show you these are the elements I already told you. And this is the entity relationship schema of IMM. Why did we do this? We did this because instead of having a very big Excel sheet that makes a lot of confusion because there are repetitions and it is rather dirty, the result will be a logical schema made of many tables. When we need data from those tables, we just join those tables together and then we make a big table that contains what we need. But we don't have only one table that contains everything, because otherwise there is a risk of errors that is very, very big, okay? So I'm just commenting a little bit on this set of elements, just to give you some hints. Then if you want, you can look at it a little bit more to understand better, and you can ask me. And again, if you're interested in something about, instead about the real project IMM, so some, there are two aspects actually. One is that the professors that work at IMM, the architects could tell you the story better than I. And also another point is that a student of mine, a PhD student of mine, is working on this, and so she could show you the examples of analysis of clusterization, data mining techniques, etc., applied to the data of IMM. If you're interested in that, you speak with Professor Baresi and we can find what to do. Anyway, just to give you an example, we spoke about these indicators, okay? But the indicator has two characteristics. One is all the data that regard the indicator in general. So what is the name? What is the description? So what is it about? What is the system? Does it belong, for instance, to the SDG indicators? Because there are some of these indicators are also indicated in the SDG Sustainable Development Goals system. How much does this indicator weigh in the sense of with respect to the if we want to improve the performance of the city, okay? And so these are the generic characteristics of an indicator. But when I measure the indicator, at a certain time it will have a value, and at a certain other time it will have another value, because maybe before the analysis I measure the indicator, then there will be a date of this measure and a value. But after the system has been, after the city has been improved, there will be more measurements of this indicator, and then with different dates we can see according to the various interventions in the city, the value that the indicator has. So you see that I have a strong entity that speaks about the indicator in general, what it means, the description to which system it belongs. But then when I have to measure it, then I will have another entity that records, another table that records for that indicator what are the values at a certain time, okay? Then, for instance, component. What is the component? Components of a city can be buildings, can be streets, can be squares, there can be green areas, for instance, of the city. And when you modify the structure, when there is an intervention, an architectural intervention to improve the city, then sometimes some components can be transformed in another component. For instance, in an area where there are too many buildings, some of the old buildings, or maybe a factory that is not used anymore, that can be transformed in a square, or maybe in a green area, okay? So one component after the intervention could produce another component, okay? And so there will be a date of the first component, and then according to some intervention that has been done, there will be the new component that raises there after some time, okay? Then these components that are the building or the square, etc., have some attributes. That means what is the shape of this component, what are the measures, for instance, what is the length of the street, what is the area covered by the building, etc. And these are the attributes, okay? And by means of these attributes, there are these metrics that are performance indicators that I'm not going to explain to you because it is too complex at the moment. But you see that the DOP are let me go again to this because a design ordering principle. So let's say that design ordering principle is a principle of design that should help modify the performance of the city. And so these DOPs are the ones that determine the actions that are done to modify these components, for instance, okay? And this action at that point, since it modifies the component, is acting on the the key categories that are the categories that I want to improve. Okay, so you see that things are very related to each other. I'm not going to go into details more than that. This is the translation. Many of these things are the ones that are timed. Some of these things are immutable in a way, because key category has a name and a description. The metric has a name and the key category to which it belongs. So these things are not mutable. While these things in gray are the mutable things that are timed. That it means we change those things in order to modify the performance of our city, for instance. Okay. So what is this for? Design a set of tables that will contain interesting data, possibly merge together only the things that I want to use at the moment of my exam, of my analysis, and not using those immense Excel sheets where a lot of mistakes could be done. The certainty that this data is of good quality if the data have been well designed, let's say. These are references to the books where you can find interesting things about what I said. And okay, feel free to ask more explanations, try and solve some of the exercises and write to me for feedback, okay? To become confident in the concept that I gave you. I'm very sorry for the people who already knew these things, and so I'm a bit, I had the idea that many of you didn't know these things, and so I explained thinking to say something new, but I hope that it was not too boring anyway. And we decided to.
Thank you, Letizia. Thank you very much for the lesson in databases, use of identifiers, attributes, and other elements needed to design the database flow. Even for me, I'm not an IT person, it was very interesting.
At least for one, I'm very happy about that.
Thank you. Ignacio has dropped here a few questions.
Ah, good.
I think he can ask himself, and
Yes,
you can reply at him.
Yes,
Okay?
you please ask.
Ignacio?
We don't hear you, Ignacio.
Yes, I'm here. Thank you,
Okay.
Professor, for your presentation. It was really interesting.
Thank you.
I've some few questions. My first one is it's not a question. Actually, I'm interested in some examples about how to use some techniques like data mining to apply this model.
Yeah.
So I'm the one who is interesting.
Yeah.
A question is this one. How do you collect, or I don't know if you have already collected the data.
We have the data, actually. What we are trying to do now is to reorganize them according to the schema that you have seen. Because for the moment, there is this enormous data set, Excel data set, where there are a lot, as I was telling you, many repetitions of things that are repeated every time, but it is not necessary because once is enough. And so let's say that the analysis that has been done, for instance, one of the examples of the analysis, and I will put you in touch with the person, my student, my PhD student who is working on it. She's called Emilia. They did, she and my colleagues from architecture, they did, for instance, some clustering application. They did some clustering to see what in Milan, given the city, the data that they have are from the city of Milan. And so they are, for instance, clustering together areas where the performance according to those indicators are similar. So that you can see that, for instance, there are some areas where for instance, the the air is particularly polluted, or the streets are particularly small, or there is no green areas at all, or it's a place where, for instance, every time it rains, there will be lots of water in the streets, and that can be not hygienic, things like those, for instance. They are grouping together, clustering together these areas in order to try to apply some of the let's say some policies to these areas, or they are for instance studying what are the areas that have more green, the quarters of Milan that have more green zones, and to see whether they perform at the same time, at the same way, or maybe even if there is a lot of green in both, there are a lot of problems only in one, and why should there be a problem only in one of these when they have some characteristics that seem to be the same? These are the kinds of analysis that they make.
Okay, thank you, Professor. So what I would like to know here is the techniques you have used to collect those data.
This is difficult because it really depends on the cities. Because there are cities, for instance, for Milan, there are a lot of data that can be collected from the municipality, from let's say official, for instance, from the company that delivers the water. They have a lot of interesting information about that. But you know that Rosinha is a favela in Rio de Janeiro, for instance, in Brazil. And these people have worked on Rosinha for a long time, together with the authorities of Rio. And there is still some kind of presidium there with a number of people from Rosinha that are still working with the help of IMM. And there, for instance, they were studying how large the streets are, how overpopulated they are, etc., etc. And some of the information is provided by the municipality, but they also installed a lot of sensors to see, for instance, how much traffic there is in one street at what time, how many people are going on foot, and how many people are going by car, and things like those, and how many people are going to school. For instance, even if there are, I don't know, 30 infants that go to the creche, there should go, but then there will be only 10 every day because the parents have problems to accompany them because they are far from all these things.
Okay. For instance, for this case of Mozambique, Quelimane, maybe using Instituto Nacional de Estatística, we'll call it.
Yeah.
I don't know if
this is something. This is interesting, Ignacio. I surely can put you in touch with my friend and colleague Massimo Tadi about that, because this was something that this was an attempt of a project that we tried together. I don't know, something like 5 or 6 years ago, and it was not funded. But I don't know whether they have kept their relationships and they have gone on that. So he has a lot of more information about that, and I can put you in touch with him surely.
Okay, thank you, Professor. I'm done.
Okay, so I don't know how if there are more questions. Okay.
Podemos ter mais alguma questão? Alguma questão mais?
Okay.
Seems like not.
No. So anyway, again, whenever you want to know something from me, you can write to me. My address, I don't know whether you know my address, but it is very simple. It has name.surname with the same address as Luciano Baresi, so it's very easy to reach me, and Ignacio knows it because he's in some of our messages, so he can give it also to the other students. And so whenever you need to know something, it will be welcome, let's say, and whenever you want explanations or something like that.
Thank you.
Okay. And Ignacio, I will talk with my colleague and I will tell him that you are interested, and so I can put you in touch.
Okay, okay, Professor, thank you.
Okay, very good. Okay, thank you very much, everybody. Roxanne, thank you very much, really, to manage this talk. And okay, till next time.
Till next
also,
time.
Also, my student and your Chiara Criscuolo, who is the person who will collaborate in this project, she is a rather expert of a number of techniques for data analysis. So maybe she can tell you a lot. Again, if she comes to Mozambique during the summer or whatever. Okay.
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 Thank you.
Bye-bye. Bye.
Pleasure.